derivative. I'm going to create the table for graphing again because I'm going to add to it. So 0, 2, and 10. C prime, we already determined that this was positive and this was negative. C of t, we have at 0, which is 0, we have at 2, which is 5.41, and we have at 10, which is 0.04. 5 if you want, 4 or 5. Okay, so now let's determine the second derivative. So this is our first derivative. This is what I'm going to differentiate. Not that, but this. So let me copy it here. So c prime of t equals 10e to negative t 2t minus t squared. Ready? Can anyone help with the second derivative? 10 stays outside. I differentiate the first function, and I get e to negative t times the inner function prime, which is negative 1, times the second function, plus e to negative t times 2, yes, minus 2t. Very good, awesome. I'm going to take out, of course, the same culprit. I don't want it in there. So it's 10e to negative t, and let's see what we have. Negative 2t plus t squared plus 2 minus 2t. Ugly. 10e to negative t, t squared minus 4t plus 2. And the question is, when is this 0? Well, I have to solve the quadratic equation, because this is not 0, this is never 0. I have to solve this equal to 0. But it's not factorable, so I will have to use the quadratic formula. T squared minus 4t plus 2 equals 0. Can anyone refresh our memory on the quadratic formula? Very good. 4 plus or minus 16 minus 4ac, 4ac over 2a. Excellent. So this is 4 plus or minus the square root of 8 divided by 2. I'm going to plug this in the calculator. I need 2 approximations anyway. Ready? Parentheses for the numerator, please, around the numerator. Left parenthesis, 4 plus the square root of 8. Okay. I broke my own rule by not putting parentheses around 8, divided by 2. And then the other one with minus. Good. So 0.6 I'm going to put 0.6 and 3.41. So t equals 3.41, t equals positive, I'm sorry, of course, 59.6. Good. Ready? So this is the second derivative. I have to determine this value and I have to determine this value, but that's okay. I can go back. I can go back to second and table and plug in 0.6 and plug in 3.41 because I need those numbers. So I'm going to say 2 and 3.8. 2, 3.8. Because I still had the function in there. Okay. So final step, I have to study the sign here and here. Why? Why am I studying the sign between 0 and 0.6? and between 0.6 and 3.41, and between 3.41 and 10. Why? What for? For the second derivative. Why? Inflection points, exactly. So here's the function. This is always positive. Don't bother with it. Always positive. So I'm going to plug in here, and I can plug in 0. When I plug in 0, what sign do I get?
Negative.
0, 0, positive 2. Good. Let's plug in 2. 4 plus 2 is 6, minus 8. Perfect. And let's plug in 10. 100 minus 40 plus 2. What do you conclude? We already concluded that here this is a local max. What do you conclude about 0.6 comma 2? It is an inflection point. The second derivative is 0, and it changes sign. So this is an IP, and this is an IP. All this procedure was discussed in chapter 2. So it carries into all chapters moving forward. We are ready to graph it. All I care about is my table. Nothing else matters. And we are only going to graph the function between 0 and 10. That's what they wanted us to do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is f of x. Ready? I will plot the point 0, 0. Let me use a different color. I will plot 0, 0. I will plot 0.6 comma 2. I will plot 2 comma 5.41. I will plot 3.41 comma 3.8. 3.41 comma 1, 2, 3, 4 here. Maybe I went a little too far. 1, 2, 3. No, I didn't go far enough. Okay. And at 10, I did not. What was it? 10 was 0.04 or something, right? So very close here. Ready? The function opens up starting at 0, 0. And at this point, it has an inflection. Opening up at this point, inflection, it will change concavity. Still opening up, opening down, still increasing to the local max. Opening down, increasing to the local max. Still opening down, decreasing to the next point of inflection. Changing concavity, decreasing to almost 0. And now we know why the calculator or the software showed me this. But it doesn't show the inflection points. It can't. From 0, 0, increasing, opening upward, changing concavity at this point, increasing to the maximum, still now decreasing, but still opening downward, hitting or having an inflection point when it changes concavity and starts opening up. Any questions? Any questions? Okay. Do I still have time? Yes. Okay. So we can start now the exponential, the log functions. Ready? We can prove that a to the x later. So let me just show one example with a to the x. And I don't see any other than the word problem. So let's work on one more problem so we don't forget. I don't want to forget to go back. So let's work on one more problem that does not have the base. Okay, stock prices, number 90, before we move on. We can prove that anytime. It's not a big deal. 90 on page 306. So one more time. When we differentiate e to the x, let's refresh our memory, we get e to the x. When we differentiate e to a function, we get e to the function times the function prime, like we always do, times the inner function prime. And what about a to the x? A to the x prime is a to the x times natural log a. We haven't discussed, that's my dilemma, till 3.2 we have not discussed natural log a. And I don't like just giving you stuff to memorize. But if you remember, before we graph the natural log function, if you remember, natural log of e is 1. So here we should be writing times natural log e. We don't, because it's 1. Here we should write times natural log e. We don't, because it's 1. But here we have no choice. So the base is not e, it's a, anything but e. So this is the way we differentiate. And of course, if we have a raised to a function, prime will be the whole thing, a to the function times u prime times natural log a. I will prove this in the next section, but I don't want to forget, I want to show you a problem. And let's do that. So here's one, stock prices, 90 on 306. The value or the price of a share of stocks in Barrington Gold was $90 plus on June such and such, and was increasing by 3% per week. Okay, find an exponential model for the value V of a share of the stock in dollars t weeks after June 15th, 2014. So I copied the information. So initially it was $90, and then it increased by 3% increase per week. So the value of a stock is the original value times 1 plus 0.03 raised to the power x, and this is v of x. Now, of course, we can combine these two. So this is 91 is the original, because it's 90 plus 90 times 0.03, but it's raised to power x. So this is 90 times 1.03 to power x. The function will be given to you. You will not have to come up with the function. I will give you the function. So what I'm interested in is part B. What was the rate of change in the value of a share of the stock 6 weeks prior to? And use the model to estimate the value of a share 6 weeks prior to June. Okay, so I'm only interested in differentiating this function and finding the rate of change. What was the rate of change 6 weeks prior to, where x is the number of weeks. Okay, so when we have to differentiate this function, the constant stays outside, 90, times, remember this is not e to the x, this is a to the x. So 1.03 raised to x times the natural log of 1.03. I don't think they should have put this problem in here. They should have waited till after section 3.2. And now the question was, so this was the rate of change, and we're asked to plug in 6 weeks prior. It says 6 weeks prior to. So we only have to determine v prime of -6. That will be the rate of change. And use the model to estimate the value. So then we will estimate the value 6 weeks prior, which means V of -6. They should have not put this in here, but they did. So let's take a look. Let's put in the function in y equals. So the function is 90, and in parentheses 1.03, caret. Please put this in parentheses at -6, although some calculators may not need that. Oh, I didn't mean that. I don't need to put it. It's just one value that we need. So 90, forgive me, 1.03 and caret -6. And then the rate of change was 90 multiplied by 1.03 in parentheses caret -6, but times natural log. But again,
Do you have to bring that down?
yes, of course. I always do that. I always forget with the software. Thank you. Natural log. Of 1.03. Okay, so the second one is the rate of change 6 weeks prior to being 90 per week. The first one is what was the price 6 weeks prior to that June 2014. That's all I really wanted you to see. We're going to come back to this. So V prime of -6 is $2.22 per week. The second one, so was $75 in 2000. What was June, right? June of 2014. So in January, 2014 in January. 6 months prior to that.
So is that the price per stock?
The price per stock, yes.
And then the
6 months before June, which is January. And this one is what was the rate of change at that time? It was increasing. It's positive.
Like $2.
Yes, in January it was increasing by $2.22 per week. Initially in January it was $75, and that's how it got to 90 in June.
Okay.
Yes. Maddie, you wanted to say something?
Sorry, I thought we were talking about weeks. Are we talking about months or weeks?
You're right. Hold on. Weeks, yes. So it's not January, it's 6 weeks prior to June 15th. So what is that? Thank you. May. Anyway, 6 weeks prior to, thank you. You're right. I don't know how I jumped to a month. Okay. Good. Section 3.2 talks about natural log and log functions. 3.2, logarithmic functions. Well, the log functions are inverse functions of the exponential. So log is the general notation, base a of x. So one more time, log base a of x. That's how we read it. Where the base has the same properties as before. It can either be greater than 1 or between 0 and 1. The same properties.
I'm sorry, log.
Log base a of x. That's how we read it. Log base a of x. This function is also kind of special. It has properties that no other function has. When we graphed the exponential function, 2 to the x, we got this, if you remember, right? A few minutes ago. The inverse of 2 to the x is log base 2 of x. Do we remember this, or I have to show it from scratch? If we say you don't remember, because I want to graph it. I want to graph log base 2 of x. If you say you don't remember, I'll show you from the beginning. The function will look like this. And they are inverses of each other. We do remember, or we don't. I don't think we do. Okay, so let's start from the very beginning. So log base 2 of x, and let's look also log base 1/2 of x. Two different functions. Like with the exponential function, log has two possibilities, with a base greater than 1, like this one, and with a base between 0 and 1, like this one. There are two very special functions, of course. Let's take a look at them for a moment. One of them is this one, log. Obviously, it shares the same key with 10 to the x. And this one is ln. Obviously, it shares the same key with e to the x. Why? Because they are inverses of each other. This and this, inverses of each other. This and this, inverses of each other. Okay. So one of them is called common log, of course, and the other one is called natural log. So if we look at log x, this is common log, where the base is 10 and we don't write it. A is 10. We don't write it by convention. Like with the square root, we don't write the index. The other possibility is log base e of x, which we don't use, but we write ln x. And this is natural log, where base is e. So if you see ln, the base is not 10, but the base is e. Natural exponential function. Natural log function, inverse of the exponential. Okay, do I have time? I have 2 minutes. Choose one of these two so we can graph it.
The second.
We want the second one. Very good. So x and f of x, and we are looking at f of x equals log base 1/2 x. Well, there is a problem with this function. This function is not friendly. It is only defined on positive numbers. So now if we'd like to plug in x values, which x values will I pick? Well, I can really pick anything between 0 and infinity. I can even pick 1/3, 1/5, 5.2, 5.9. I can plug in anything. However, and I'll show you next time why, I'm going to pick powers of 1/2. I'm going to say 1/16, 1/4, 1/2, 1, 2, and 8. So in y equals, I have to show you a property in order to determine those by hand. And I didn't get the chance to. And I don't want to hold you over. So the function is log base 1/2. Well, my software may have, I'm not sure if it does. It does, I don't think it does. Some of your calculators may allow you to put in the base you want. My calculator does not. So I have to change the base. So I will have natural log of x at the top and divide by natural log of 0.5, which is 1/2. I'll show you the formula. And second and table, and that's how I get all those numbers. With 0, with 1/16. I'll stop. I will not graph it today for you. We'll finish it. So with 1/4, with 1/2, of course with 1 and 2 and 8, and so on and so forth. So we will plug in these numbers, and we'll graph the function so we can see it. We ran out of time. I'm really sorry. It's a lot of